Okay, so finishing off chapter 6, suppose I have a chart of data and I think it's modeled by a sinusoidal function. Can I find out what that function is? So can we fit a sinusoidal function to the data in this table? Well, let's check. A scatter plot suggests maybe, yeah, this could look like a sine function. So let's pretend it is, okay? We want to find the amplitude. This is usually the easiest thing first. So take the biggest value minus the smallest value over 2. Okay, this is just the max minus the min over 2. We actually did a similar computation in an earlier problem. The max minus the min over 2 gives you the amplitude. Back on that chart of data, the maximum was 74.2 and the minimum was 30. So we get a suspected amplitude of 22.1. Okay. So here is a graph of 22.1 sine x. It really doesn't look the same. Okay. So we need to accomplish some horizontal shifts and compressions and vertical compressions and shifts to try to get this correct. Sorry, we don't need another vertical compression. We already got the amplitude right. Okay. The vertical shift, remember, is the median value, which is the average of the highest and lowest values. So we already determined the highest and lowest values to be 74.2 and 30 with an average of 52.1. That tells me my vertical shift should be 52.1. Okay, this actually looks a lot better. We have the same basic range between max and min. It's just the period and the horizontal shifting look all wrong. So we need to accomplish that. So let's work with the horizontal stretch factor, aka the period. Okay. We reasonably conclude that temperature is going to repeat itself every year, every 12 months. So the period should be 12. So since 2 pi over omega is 12, we conclude omega is probably pi over 6. Okay, so if I put omega equals pi over 6, now we have the right period, but the horizontal shift is definitely off, aka the phase shift. Okay. So to determine the horizontal shift, we're going to determine a quarter period. If the period was 1 year, a quarter period is 3 months. And there they are, 0 to 3, 3 to 6, 6 to 9, etc. The sine curve increases from 0 to 3 and then decreases on 3 to 9, etc. So local maximum would normally occur at x equals 3. But our local maximum occurs at x equals 7, July. So I want to shift 4 units to the right. So I replace x with x minus 4 to do a shift 4 units to the right. And if I distribute that pi over 6, we get phi is equal to 2 pi over 3. And now if we plot it, it is quite a good match. So it's fundamentally the same skills we were doing on the previous examples of match a picture and figure out the function. You identify things like max and min and period and extract the relevant curve. Okay. So amplitude is max minus min over 2. Vertical shift is max plus min over 2. The period can be determined by how long it takes to repeat, and then solving that period is 2 pi over omega, and then solve for omega. Then you just have to shift your data so that the maximum occurs where you want it to. Okay, so let's do another example. Okay. The number of hours of sunlight in Boston, okay, at summer solstice, aka the most sun, is 15.28 hours of sun, and at the winter solstice, aka the least sun, it's 9.07. So go, that's it, that's all your data. Match it with a sinusoidal function. Now if we had the sinusoidal function, we could plug in specific days to predict the sunlight. So let's work through this. All right. The amplitude is max minus min over 2. We were given the max and the min, so we get the amplitude is 3.105. And the vertical shift is max plus min over 2, the average. And we compute that to be 12.175. So if we're going to use a sine function, we already know the amplitude and the vertical shift. Also, assuming that the data repeat year, and this time we want to measure it in days, because later on we were specifically told to plug in a day and try to determine what the sunlight length is. So we suppose that the period is 365 days, so we solve for omega as 2 pi over 365, which we put right there. Okay. All we have left to do is determine the horizontal shift. Normally, we would expect the horizontal shift the maximum, to occur at 1/4 period in. However, the longest length sunlight is the summer solstice. But the summer solstice is at day 172. It's June 21st. This is 172 days into the year. So instead of occurring the maximum at 91 1/4, we need it to occur at 172, which means we need to shift by 80 3/4 units to the right. So we do that. And there we have a sinusoidal function that matches all the data we were given. So now, can you predict, oh, you can multiply the 2 pi over 365 out if you want. It's really quite optional. But there it is. So can you predict, sorry, I should leave it up here so you can copy this function if you need to. Okay. The next step is, can you predict what the amount of sunlight is on any particular day? Okay. So on April 1st, you just have to figure out how many days into the year that is. It's 91 days into the year. I believe the book. So just let x, the number of days, be 91 and punch this into a calculator, making sure you're in radians mode, by the way, and you'll end up with 12.72. So 12.72 hours of sunlight, which is about 43 minutes, that's 0.72 hours, April 1st in Boston. Neat. Here's the graph. Okay. Sunlight hours really is quite sinusoidal. There's a little bit of a shift compared to a pure sine function. And it's from a couple of different factors. So here's the Earth with the equator. It's at a slight tilt, and the sun is back here. So different latitudes will have different amplitudes of this function and vertical shifts. Extreme latitudes have higher amplitudes because you can have, actually at above a certain latitude, you can have more than 24 hours of consecutive sunlight. But let's assume we're not that extreme. Very far north, you can have close to 24 hours of sunlight during the summer and close to 24 hours of darkness in the winter. So the amplitude is quite extreme. Down on the equator, it's closer to 12. But if the orbit of the Earth around the sun were a perfect circle, a perfect sine curve would be what you actually got. The orbit around the sun is not actually a perfect circle. It's actually an ellipse that's almost a circle. It's just barely not a circle. So since it's just barely not a circle, it's not actually a sine curve. It's a modified sine curve, an elliptical sine curve. But hey, for most purposes, a sine curve is close enough. Sorry, continuing. So supposedly it would have been 12 hours and 45 minutes of sunlight, which is pretty close to what we predicted. We predicted 12 hours, 44 minutes and change. Okay. I'm a little peeved that their next example still has temperature or sunlight, which are yearly periods. I'm going to do an extra example later where the period isn't a year. So can we look at this chart of data, enter it into your calculator, and do a scatter plot? So pause here to enter it all in. Okay, so if we scatter this, we can do what's called a sinusoidal regression. This cuts out a lot of the guesswork as long as you're just doing a calculator-based approach, and it's just going to tell me the amplitude A. They don't call it omega, they call it B, and they don't call it phi, they call it C, but basically it gives you all the terms there for your sinusoidal function. I think the notation here is out of the TI-83. And it'll just spit out that function, and the sinusoidal regression, if you do it on that chart, just tells me this, and it plots pretty nicely. So let's actually go to a blank screen here so that I can do an example where the period isn't a year. So let's do an example of tides. Okay. Hey there. Sorry, I accidentally changed what screen I was looking at. We're doing tides. Okay. So suppose you measure the tidal depth at, let's say, 12:16 a.m. You have a low tide with a depth of 1.8 meters. The next high tide occurs at, it's approximately a 12-hour cycle. So let's say it's at time, let's go with 12:04 p.m. You get a high tide. And let's say, I don't actually know what's realistic for tidal movement, but let's just put something in here. Let's call it 8.1 meters. So predict the tide at, let's say, 6:15 a.m. the next day. Okay, so we've been given some information. Not a lot, I'll admit, but some. Sorry, I'm just pulling out a piece of paper. That's what that noise is. So what we've been given is, let's measure time in minutes. So at 16 minutes past minutes, we'll call that t equals 16. We have a height of 1.8. Next, we need to determine what time is 12:04 p.m. Well, it's 12 hours past midnight. That's 720 minutes, and then 4 more minutes. So at time 720, we have 8.1 meters, and that's the next high tide. Okay, and then what we want to do is predict 6:15 a.m. the next day. So if I'm measuring time in minutes, this is t equals 16. This is t equals 724. And we want to predict it at 6:15 the next day. So a day is 24 hours, which I multiply by 60 to get 1,440 minutes. Then I need to do 6 more hours. That's another 360 minutes. But then another 15. So overall, we are looking at 1,815 minutes. Okay? So we are given the value at t equals 16 and equals 24. We would like to know what is the value at t equals 1,815. So I'm going to erase all of this and start marking up a function. All right, so we are looking for something that goes from a minimum to a maximum, and the minimum occurred at 16, 1.8. The maximum occurred at 720, 8.1, 724, 8.1. Now what we want to do is match this to a sinusoidal function. You actually have a lot of freedom. Okay? If I pretend the graph starts here, then it looks like a positive sine function. But if I pretend the graph starts here, which is really where our graph has started, it looks like a negative cosine function. If I started the graph back here, it could be a negative sine. If I started the graph back further, it could be a positive cosine. You really just have to arbitrarily decide where this to start. And I'm going to start it here. So we are looking for a negative something cosine of omega t minus phi plus a vertical shift. And now we just need to figure all of this out based on the information we were given. And now you can see it's very similar to stuff that we've had before. So let's determine our amplitude. So we know that amplitude is max minus min over 2. We also know that our vertical shift is max plus min over 2. Okay, max minus min over 2, 8.1 minus 1.8 is 6.3. So if I divide that by 2, we get 3.15. Okay, max plus min is going to give me 9.9, and if I divide that by 2, 9.9 over 2 is 4.95. So I come down here and I say my amplitude is now 3.15. My vertical shift is 4.95. Great. Next, we need to determine the period. Well, how long did it take us to go between these two? How many minutes? 724 minus 16 is going to be 708 minutes, and that is a half of a period. It went from minimum to maximum, but didn't come back down. So I say, doubling that gives me 1,416 minutes is a full period. Okay, so 2 pi over omega needs to be 1,416. from which I deduce that omega is 708 over pi. So I come down here and I say, great, omega is 708 over pi. So I'm going to copy down what we have so that I can erase everything, and then we can work on finding the phase shift and predicting the value. Okay, so we have negative 3.15 cosine of 708 over pi times t minus an unknown phi plus 4.95, and our two given points are there. Okay, so I'm going to clear everything off. Hopefully you copied it down as well. Okay, I'm going to do it. Here we go. So here's what we have so far. We know that y is negative 3.15 times the cosine of 708 over pi times t. We still haven't determined our shift phi, plus 4.95. And the points that we were given were this minimum and this maximum at 16, 1.8 and 724, 8.1. So we have a negative cosine curve. We have a negative cosine curve that would normally start at 0, but instead we have shifted 16 units to the right. So if I actually replace this with the 708 over pi factored out, I can immediately just say this, 16 unit to the right shift. And there we have it. There's our function that predicts tidal depth. Finally, we were asked predict at t equals 6:15 the next morning. We determined was, oh, I didn't copy that down. I'm silly, I'm gonna have to figure out again, sorry. So a full day was 1440, then 6 hours was 360, and then another 15. So we need to determine this at t equals 1850. So all we need to do is plug 1815 in here. So I'm just going to pull out a calculator on another tab to predict the tidal depth. So negative 3.15 times the cosine of, and make sure you're in radians mode, 708 divided by pi times the quantity, 1,815 minus 16, and be judicious with your parentheses. You don't want to skimp out on them, plus 4.95 for a predicted tidal depth of 1.805. Okay, so there it is. Cool. Cool. Stop. How do I stop the video? There it is.